Hey everyone, welcome back yet again, and thanks for joining us in our discussion of conditional probability and the general multiplication rule. Heading into our objective about computing conditional probabilities, we're going to do a quick conditional probability introduction. We have some language to understand here. First, the notation we see is read the probability of f given e. So that vertical line you see represents the word given, so it's the probability that event f occurs given event e has already occurred. This is a big concept to understand though, because that means event E is in the past. It's something that has occurred, and we are looking for the probability that F occurs given that E has already occurred. And of course, we'll apply that to some examples. Taking a look at this example real quick then. Suppose that a single-sided die is rolled. What's the probability that a die comes up 4? Well, according to our classical method, we know that there is 1 4 out of the 6 options of this single die. That means the probability of rolling 4 would be a 1 over 6. Now suppose that the die is rolled a second time, but we have cheated the die. So we know the outcome will be an even number. What is the probability that the die comes up 4 now? Well, of course, this is the big deal that we know the outcome will be an even number. If that's the case, instead of 6 options, we have only 3 options. We still only have 1 4 on the die. However, instead of the 6 possible sides that will happen, we only have 3 possible sides that will occur, so the probability would be 1 over 3. The concept here is the fundamental principle that the conditional probability changed the sample space. That's what conditional probabilities do. They change the sample space, and then we reassess what is the probability of some event after the sample space has changed. Well, for the first roll, our sample space S were the 6 numbers 1 through 6. However, for the second roll, the sample space changed to be only the even numbers, thus being only 2, 4, and 6, and that's why our probability went from 1 over 6 to 1 over 3. We only had 3 options, or outcomes, in our sample space. Well, that takes us to our next example then, where we're going to use these conditional probabilities, but we're going to be given this table to kind of compare, with the emphasis that we're looking to see how the sample space changes based on the question. Well, first we're told a survey was conducted in which about 1,000 adult Americans were asked, which of the following statements comes closest to your beliefs about God? 1, you believe in God. 2, you don't believe in a God, but you do believe in a universal spirit or higher power. Or 3, you don't believe in either. We have the results of the survey split by the region of the country that are given to us by the table. Let's take a look at part A then. We're asked, what is the probability that a randomly selected adult American who lives in the East believes in God? Here's the overall idea here. You see it in bold, and of course it won't be in bold on the exam, but when they say a randomly selected adult American who lives in the East, that means their location of living is not in question. Instead, we are told they live in the East, therefore that is our given information, and that turns this into event E, and we're trying to find the probability that someone who lives in the East believes in God. Well, the probability that someone believes in God means that the believing in God part would be our event F as we translate it to this conditional probability. That is, we're trying to find the probability that someone believes in God given that they live in the East, and we're trying to start to understand this language where we translate that to be, alright, the probability of F, someone believing in God, given that event E, they live in the East, has occurred. Well, taking a look at our table then, the first column of our 4 regions are those who believe in God, and that's what we're looking for. However, since it was given that they live in the East, it means that we're basically ignoring everyone who does not live in the East. That is, as we go to answer this question, we are ignoring the table now of all the data for those who do not live in the East. Instead, we're only looking at our table for those that live in the East, and thus our sample space has changed. Our original sample space had 1,017 adult Americans. Now, under the conditional probability, we are only considering 255 of these Americans, and to calculate our probability, we find out how many of those 255 Americans believe in God. Well, we have 204 people who said they believe in God out of the 255 total, therefore our probability ends up in a 0.8. That is, according to our results, about 80% of people believe in God given that they live in the East. Again, the overall theme there is we had our original sample space, that was the full 1,017 people. However, after the conditional probability was given, we looked at only those who were living in the East. Let's take a look now at part B. Or ask what is the probability that a randomly selected adult American who now believes in God lives in the East. Make sure you're careful here. We chose this on purpose. Comparing this to Part A, the given information in Part A was that people lived in the East. Now they're telling us that we know people believe in God. That means those who believe in God would be the given aspect of our probability, and the question of living in the East becomes our event F, the probability that we're looking for, given that we already know E, they believe in God. Taking a look at our table then, we have our full sample space, but we're finding the probability of a randomly selected adult American who believes in God. That means we are only looking at those who responded that they do believe in God, and that means we are ignoring or changing the sample space by ignoring everyone who has responded with anything besides believing in God. Now that we have our given, and these representing event E, they're asking us what is the probability that a randomly selected adult American lives in the East. This means one more time we're looking at the number of people who live in the East, but the sample space has been changed to be only those who believe in God. We have 204 people yet again who live in the East. However, our sample space would be the total number of people who believe in God, and that total would be a 787. Therefore, the probability that someone lives in the East, our event F, given that we know they believe in God, our event E, would be those 204 people who live in the East and believe in God out of the 787 people who say they believe in God. And we end up with a probability of approximately 0.2592. And we're all set with our conditional probabilities when we're given our table of data. And now that we've discussed a couple examples, it begs the question, what is the actual conditional probability rule, mathematically speaking? The conditional probability rule states that if E and F are any two events, then the probability of F occurring, given that E has occurred, is the probability that E and F occurs divided by the probability that E occurs. Well, if that's tough to follow, we could also think of it as the probability of F given E can be found by figuring out the number of ways that E and F can occur, or the number of outcomes that satisfy both E and F, divided by the number of ways that just E occurs. Just quickly referring to the previous example, this was our 204 people that lived in the East and believed in God, divided by, in that last example, were the 787 people who believed in God. In the example before that, we still had our 204 people who lived in the East and believed in God, but we divided it by our 255 people who lived in the East. So since we were talking about people living in the East and believing in God in both examples and just switching which one was given, the 204 stays the same, while the sample space, the number of ways that that given aspect occurs, changed. If that's okay, let's take note to a big deal over here. If P of F is not equal to P of F given E, then the two events are not independent. This is a little bit tough to follow at the moment, but what we're saying is, if we found the probability of F occurring, and that's different than the probability of F occurring after E occurs, then they must not be independent based on the definition of independence. Remember, if two events are independent, then the probability of occurrence of one does not affect the probability of occurrence of the other. However, if these two guys are not equal, that means the probability that event E occurs does have an effect on the probability of F occurring, therefore they must not be independent. If they were independent, then these two would be equal because it wouldn't matter if E occurred or not. P of F would be the same as P of F after E has already occurred. We'll bring this up again though in future examples. Heading into our next example then, we're stepping it up a notch as it gets a little more sophisticated. In 2005, we're told that 19.1% of all murder victims were between the ages of 20 and 24 years old, and 16.6% of all murder victims were 20 to 24-year-old males. They ask us, what is the probability that a randomly selected murder victim in 2005 was male, given that the victim is 20 to 24 years old? As soon as we see the words given that, we need to be thinking conditional probabilities. That's the toughest part of these guys though, would be recognizing which aspect is given and which aspect are we looking for. Since the problem says given that the victim is 20 to 24 years old, that means the age aspect would be the given information. so we get to call the age aspect event E. Going back to the first sentence then, that means we know again the age aspect is event E, and that also lets us know that the 19.1% would be the probability of E, because it tells us that 19.1% of all murder victims, out of everyone, that is, the full population of murder victims, were between the ages of 20 and 24. Well, right now we're trying to find the probability of F given E, which means we can use our formula to find that probability. We know the formula says it's the probability that E and F occur, and divide that by the probability of E. We've addressed that we have the probability of event E. Now we just need to recognize we need the probability of event E and F. Looking back at that first sentence, it's a little bit sneaky because we don't get to see the word and. However, that last bold part says all murder victims were 20 to 24-year-old males. This is our E and F. It's because we have the age, event E, and the gender, which would be males. 20 to 24 years old and male would be this category that's being discussed. That means the 16.6% that was given would be the probability of E and F. It says 16.6% of all murder victims. The of all murder victims tells us we're still discussing the entire population of murder victims, not some smaller sample space. Since it's everyone out of all of these guys, it's the event E and F. It's the age and the gender that's also being discussed, so that's our E and F. That means to find our probability, we can take our 16.6%, which we write as 0.166, divide that by the probability of event E, our 0.191, given to us as the 19.1%, and we end up with a probability of approximately 0.8691. Which means we're all set with finding our conditional probability here. Let's make sure we recognize that in this problem, we were only given two numbers. So we had to find the probability. They only gave us two values here that we would be using, but it will get more sophisticated than that as well. There will be some distractions in there, like 2 or 3 or 4 numbers. It won't be as straightforward as, okay, even if I don't know how to do this, I know there are only two numbers. I need to either multiply them or divide them. Sorry, but it won't be that easy to deduce. I say that to make sure we focus on the concept. Again, the concept was trying to recognize which event was given and which event would be qualifying as event F, the probability that we're looking for, given that E has occurred. Continuing on to our next example then. We're told for the month of June in the city of Chicago, 37% of days are cloudy. Also in the month of June in Chicago, 21% of the days are cloudy and rainy. We're not sure what they're asking yet until we hit this sentence. What is the probability that a randomly selected day in June will be rainy if it is cloudy? This sentence is a big deal. We have to be real careful with our reading. The key part of it would be the if it is cloudy. That establishes what aspect would be our given event E. We're only trying to find the probability that a randomly selected day is rainy if it is already established that it's cloudy. Thus, the cloudy aspect is given, and that also establishes that the rainy aspect is our event F, because that's what we are looking for, the probability that a day is rainy, given that it's already established as cloudy. If that part's okay, now we're just looking into the idea of, okay, what's our probability of event E? What's our probability of event F? And of course we know the probability of event F given E, which is what we're looking for, would be our probability of event E and F occurring divided by the probability of our event E. Trying to find those values within the problem, we're told that 37% of the days are cloudy. We established event E as cloudy. Therefore, the probability of event E is our 37%, which we write as our 0.37. And then we're told that 21% of the days are cloudy and rainy. Therefore, that 21% represents the probability of E and F. Keyword in between those would be and, of course. It's cloudy, our event E, and rainy, our event F. Therefore, we have our P of E and F at a 0.21, and we get a probability of approximately 0.5676. And we're all set one more time with finding our conditional probability.